Everyone, so today we'll be discussing angles and their measures, trigonometry of right triangles. So for today, the word trigonometry based on the Greek word for triangle measurement was first used as the title for a text by the German mathematician Pitiscus. Originally, the trigonometric function were restricted to angles and their applications to the indirect measurement of angles and distances. So trigonometry is a branch of mathematics which deals with measurements, or more specifically with the indirect measurement of line segments and angles. The sum of the interior angles of a triangle is 180 degrees. Classification of triangles according to angles. We have oblique triangle, a triangle with no right triangle. It is either a acute or obtuse triangle. Right triangle is a triangle with a right angle, and equiangular triangle is a triangle with equal angles. Scalene triangle is a triangle with no two sides equal. Isosceles triangle is a triangle with two sides equal, while equilateral triangle is a triangle with three equal sides. An angle is formed by rotating a given ray about its endpoint to some terminal position. The original ray is the initial side of the angle, and the secondary is the terminal side of the angle. The common endpoint is the vertex of the angle. Classifications of angles. So zero angle, the theta or the angle is equal to 0 degrees. Acute angle, the theta is greater than 0 degrees but less than 90 degrees. Right angle, theta is equal to 90 degrees. Obtuse angle, theta is greater than 90 degrees but less than 180 degrees. Straight angle, theta is equal to 180 degrees. Reflex angle, theta is greater than 180 but less than 360 degrees. Complex angle are angles that are greater than 360 degrees. So complementary angles are two angles that their sum is equal to 90 degrees. While supplementary angles, their sum is equal to 180 degrees. For example, by solving this, we have to find the complement of 50 degrees. All we have to do is to subtract 50 from 180, giving us 50 from 90 will get us 40 degrees. For the supplement of 110 degrees, we just simply subtract 110 from 180. We get our supplementary angle is 70 degrees. Next, find two supplementary angles such that the first angle is twice as large as the second angle. So this is an algebra question involving geometry. So all we have to do is to understand our problem. It is stated that the first angle is twice as large as the second angle. So that means that if our variable for the second angle is x, therefore our first angle should equal to 2x. And they are supplementary angles, and if we add them, we have 2x plus x is equal to 180, giving us 3x is equal to 180. Dividing both sides by 3, we get x is equal to 60. Therefore, our two supplementary angles are 2x is equal to 2 times 60 is equal to 120 degrees, and our x is equal to 60 degrees. If we add them, we get 180 degrees. So therefore, they are supplementary to each other. It is important not to confuse that an angle with its measure in our previous angle theta is a rotation, and the measure of the rotation is 60 degrees. A central angle is an angle with its vertex at the center of a circle. When the intercepted arc's length is equal to the radius, the measure of the central angle is 1 radians. So degrees is 1 over 360 degrees of a complete revolution denoted by degrees. Radians is measured by the central angle subtended by an arc whose length is equal to the radius of the circle denoted by a rad. Our formula for radians, if we have S and R, is simply S over R, wherein S is our arc length and our R is our radius. So again, from our circles, so if we have a circle and we have two radius, and the subtended arc on this radius is what we call our arc length. So this will be our arc length, or our S. our arc length or our S. And this is our R. And to solve for the theta, wherein theta is in radians, we have theta is equal to S over R. And the units for our angle here is not in degrees, but it is in radians. Quick note, if you can observe from this, we have S. The units of the arc length, we can say that it's possible that it is in meters, since it is a length, and our radius could also be in meters. If we cancel out our units, it will be unitless. So in higher math or in college, we sometimes denote radians is used, especially when we are dealing with circles, if we cancel out all the units, okay, when we are dividing or multiplying units. The units will become radians since there will be no other units left. That's why we use radians. However, in circles, it's just a denotion from us, since radians is commonly shown or commonly used when two units are cancelled out from a formula. Radians is just simply another way of representing an angle, another measurement of an angle. We're in the conversion factors that we have 2 pi is equal to 360 degrees. 2 pi radians is different from 2 pi, okay? 2 pi radians is the angle that is equal to 360 degrees, while 2 pi is simply equal to 2 times 3.14. So when you are writing it in your solution, please don't forget writing radians, because 2 pi radians is different from 2 pi alone. So it is also equal, 2 pi is equal to 180 degrees. So when we are converting, please don't memorize these formulas. Please remember when you are converting from your units. For example, we have a unit of 100 centimeters. We all know that for every 1 meter, we have 100 centimeters. So if you convert 100 centimeters to 1 meter, we just simply write for every 1 meter, we put here 100 centimeters. So we always put on the denominator the given units, and we put on the numerator the units that we want to achieve. So cancelling out 100 centimeters, we will get 100 centimeters converted to 1 meter. So we will get 100 centimeters is equal to 1 meter. There you go. So for example, we have, so what is the measure in radians of a central angle theta that intercepts an arc length of 6 centimeters on a circle with a radius of 2 centimeters? So using our formula, so we are tasked to solve for the measure in radians of a central angle. So theta is equal to S over R. So we have our S, or our arc length, is equal to 6 centimeters. And our radius is equal to 2 meters. So since they are not on the same measurement, units, we have to convert one of them. So let's convert meters into centimeters. We all know that for every 1 meter, we have 1,000 centimeters. 100 centimeters, So solving for this, we get, when we cancel out the meters, we will have 6 over 2, we will have 3 cm times 1 over 100 centimeters. So now, our answer is 3 over 100 is equal to 0.03 radians. Or simply 0.03 rad. It's just the same. Wherein theta is equal to that. So next, for number 2, we have What is the measure in radians of a central angle theta that intercepts an arc length of 12 millimeters on a circle with radius 4 centimeters? So we have again theta, we have S over R. We're in our arc length. Arc length is equal to 12 mm, and our radius is equal to 4 cm. So let us again convert our denominator. So again, we all know that for every 1 cm, we have 10 mm. So now we can now convert. So we can cancel out our units, giving us 12 divided by 4. We have 3 mm all over 1 over times 10, 1 over 10 mm, giving us for this we have 0.3 mm, 0.3 radians, or simply rad. So next, convert the following measure to exact radians measure. So we have for our number 3, we have A is equal to 30 degrees. So we all know from our conversion a while ago that for every 180 degrees, we have 1 pi radians. So converting this, we have 30. We will get 30. We cancel out, we will get 1. And when we divide this, we'll get 6. So giving us pi over 6 radians. 6 or pi over 6 rad. For letter B, we have 225 degrees. So if we convert this, we have again pi over 180 degrees. So first, if we don't have our calculator, we can first divide both of these numbers by 5 to get the most simplified value. So dividing 225 by 5, we will get 4, and then we have 45. Dividing by 180 divided by 5, we will get first 3. We will first get 3, and then 35, right? 15, yeah, 36 I mean. So from this, 45 and 36 are both divisible by 9. We can divide both of them. So 45 divided by 9, we get 5. This is divided by 9, we get 4. So this will be our lowest term, which will be in radians. Or simply pi rad. 5/4 pi rad. There you go. Next, convert the following degrees to exact radians measure. So we just have to do the complete opposite of what we've done here. So we have for letter A, or letter C I mean, we have negative 120 degrees. So it's just the same, I mean, sorry, so the opposite. So again, we have pi over 180. So we will get 120 degrees over 180 degrees. We can divide them both by 6. By 60, I mean. Giving us 3. And we get 8. I mean, giving us 2, and here is 3. So we will have negative 2/3 pi radians. Next, for letter D, we will have 472 degrees all over pi over 180 degrees. So dividing both sides first. If we can't get any number, let us first look at their units digits. So they are both divisible by 2 since they are even numbers. So dividing both numbers by 2, we will get for 472, we get 236 all over. When we divide 180 by 2, we get 236 over 90 pi. They are again divisible by 2. We will get 1 8 all over 45 is equal to pi. And they don't have any more divisibility that is common to them. So this will be our final answer. Next, for number 4, we are tasked to convert the following radians measure to exact degree measure. So first we have pi over 4 and 2 radians. So they are both in radians. So for number 4, we have for letter A, we have pi over 4 radians. So again, we have for every 1/8 degrees, we have 1 pi radians. Converting this, we will get simply, we cancel out our pi and our rod. So we will have 180 over 4. 180 divided by 4 is simply 35 degrees. Right? 35 degrees. 4, 8, 12. 16, I mean, sorry. 4, 8, 12 is 45 degrees, I mean, sorry. Next, for letter B, 2 radians or simply 2 rad. So we have 180 all over pi radians. So on here, we will simply cancel out the radians, the rad I mean, and we will get is equal to 360 pi. So if you're not using your calculator, will be our final answer. However, if we use our calculator to find the exact value, it will be 114.65 degrees. Next, convert the following measure to exact degree measurement. So again, for letter C, we have negative 5 pi over 6. This will still in radians. So again, we have our conversion, which is 180 degrees over pi. So we just simply cancel out rad, pi, and we will get negative 5 over 6. So we can simplify this. Dividing this, we have 1 divided by 6, and dividing this by 6, we have 30. So giving us negative 5 times 30 is simply negative 150 degrees. And next, for letter D, we have 3 pi over 2. 3 pi over 2 radians. So we multiply again by 180 degrees all over pi rad. So cancelling out the pi and the radians, we will get, if we divide this, we will have 1. And dividing 180 by 2, we get 90, giving us an answer of 9 times 3 is simply 270 degrees. So this will be our final answer. Next is angles in standard position and co-terminal angle. So an angle is in standard position if its vertex is located at the origin and one day to the positive x-axis. So it should be, the rotation is counterclockwise. So if we have a Cartesian plane or the x and y axis, it is a standard position if our angle is starting from the vertex and its initial side is on the positive x-axis. So if the rotation is counterclockwise, this is positive, and if the rotation is clockwise, this will be negative. So coterminal angles are angles that their sum is equal to 360 degrees. Or simply they have the same initial and terminal side. So an angle standard position if its vertex is at the origin and the initial side is along the positive x-axis. So a quadrantal angle is the angle for every quadrant. So for example, for the first quadrant, this is a quadrantal angle. Next, this also is a quadrantal angle, and next, this is also a quadrantal angle. If the terminal side does not lie along a coordinate axis, then the angle is often referred to in terms of the quadrant in which the terminal side lies. So coterminal angles are in standard position having the same terminal sides. Given theta in the standard position with measure x degrees, then the measure of the angles that are coterminal with the angle theta are given by x plus k is equal to 360 degrees. X degrees plus k times 360 degrees. So So to find the measure of the smallest non-negative coterminal angle of a given angle measured in degrees, you may follow these procedures. If the given angle is positive, subtract 360 degrees repeatedly until the result is a positive angle less than or equal to 360 degrees. If the given angle is negative, add 360 degrees repeatedly until the result is a positive angle less than or equal to 360 degrees. Similarly, if the angle is measured in radians, subtract or add equivalently 2 pi until the result is a positive angle less than or equal to 2 pi. So now, for example, this given. So we have 750 degrees. So this only means that from this angle, from our initial side, it rotated 360 degrees. And again, it rotated 360 degrees. Giving us, if it rotated 2 times, so we have 360 plus 360. This will be equal to 720. And therefore, to find another its coterminal angle, it will be to find its to become 750 degrees, it rotated again another 30 degrees. Okay, so now it rotated a total of 750 degrees. So for us to find its coterminal angle, all we have to do is subtract the 60 to it repeatedly. So giving us 750 minus 360, we will get 600. Giving us 300. Am I right? Yes, 390 degrees. Okay. And next, subtracting it again by another 360, we will get 30 degrees. So again, if we will look at our graph, so for here, if we measure it like this, so this will be our coterminal angle. Okay, so this will be the smallest coterminal angle, and this one from the orange part, this will be its larger coterminal angle. Okay, so since we are tasked to find the smallest coterminal angle, this should be equal to 30 degrees. So if we can see, it just rotated 2 times. Okay, it rotated one time for 360 degrees and another time for another 360 degrees, and then the remaining angle is 30 degrees. Okay, so however, if it rotated another larger angle, for example, if it rotated another, let us say, if it rotated another 190 degrees, then therefore the coterminal angle should be the opposite one, which should be this red one, since half of the rotation is 180 degrees. Since 190 is greater than 180, therefore the other half should be less than 180 degrees. So therefore, this should be the other coterminal angle. So let us try to prove this theory on another example. So again, for negative 600 degrees, so let us rotate this negative 600 degrees. So for this angle, we have negative 600. So if we have a negative, we just simply add a positive 360 degrees. So we have 360. So when we add 360 degrees, we will get 500. We will get 230 degrees. A negative 230 degrees. And then again, if we add another 360, we will get 130 degrees. Is it correct? Oh, sorry, it should be negative 240. My bad. So we will get here, we will get negative 120 degrees. Right? Yeah. A positive 120 degrees. So therefore, this will be our final angle. So if it's clockwise, it just simply rotated on the opposite side. It rotated clockwise if it is a negative angle. So it rotated once, again, it rotated once, 360 degrees. And then it rotated another one, 360 degrees. it rotated another from 360 degrees. It becomes negative 600, so it needs still negative 240 degrees. So negative 240 degrees. So let us say it reaches this third quadrant, 240 degrees. So since this is 240 degrees, its coterminal side should be this one. Okay? So we all know that since it rotated another 240 degrees, this is 360. This is 240. If we add 360 and 240, we get 600 degrees. So our last rotation is 240 degrees. So its coterminal angle with 240 degrees should be equal to 120 degrees. For it to be a total sum of 120 plus 240 is equal to 360 degrees. Okay? So if we graph them, this will be its solution. However, since there is a step-by-step way on how to solve it by simply adding or subtracting 360 degrees, it will be easier. Next, for 11 pi over 3, so determine the smallest positive measure that its coterminal with each of the following angles. So instead of adding or subtracting 360 degrees here, we simply add or subtract 2 pi. So we have 11 pi over 3. So I do hope you still remember your fraction. 11 pi over 3. So this one should be, the angle should be less than or equal to 360 degrees. So here we simply subtract 2 pi. So for this to be subtractable to each other, first we need to convert 2 pi to be same, to have a fraction over 3. So all you have to do is, when you have this kind of fraction 3, you just simply multiply 3 to the 2 pi, giving us 6 pi. And therefore we will have over 3. And 6 pi over 3 is simply equal also to 2 pi. So there you go. So now since we have this, we can simply divide this, simply subtract. We will have 5 pi over 3. So since 5 pi over 3 is less than 360 degrees, or less than 2 pi, so if we try to convert this, we will have 1 and 2/3 pi, or simply 1.66667, or simply 1.675. So this is less than or equal to 2 pi. So this will be our final answer, 5 pi over 3. So next, let length of a circular arc. Let R be the length of the radius of a circle, and theta be the non-negative radian measure of a central angle of the circle. Then the length of the arc S that subtends the central angle is S is equal to R theta, where theta is in radians. So this is just the same just a while ago. Okay, so from our formula, we have theta is equal to S over R. So solving for S, all we have to do is multiply both sides by R, giving us S equal to theta times R. So this will be our formula when solving for our arc. So here in our problem, it is stated that an international space station is in a approximately circular orbit 400 kilometers above the surface of the Earth. If the ground station tracks the space station when it is within a 45-degree central angle of the circular orbit above the tracking antenna, how many kilometers does the ISS cover while it is being tracked by the ground station? Assume that the radius of the Earth is 6,400 kilometers, round to the nearest kilometer. So now, if we draw our figure, we will have a circular arc, a circular motion of the ISS. So it is stated that is subtended on a 45-degree angle. 45 degrees. Okay? So this, since 45-degree angle, we can now solve for it. So we can solve for this 45 degrees, and given again our given of our radius, which is equal to 6,400 kilometers. However, it is stated that in the problem, this circular path of the International Space Station is 400 kilometers above the Earth. So for example, this blue, let's try to draw a blue circle. So this blue circle represents our Earth, and the distance, sorry, this is wrong. Let's put our label properly. So again, it is stated in the problem that the radius of the Earth is approximately 6,400 kilometers. So this one is the measurement of the 6,400 kilometers. 6,400. And the distance between the Earth and the circular path of the ISS station is 400 kilometers. And this angle is equal to 45 degrees. So we are tasked to find for this side, for this arc, I mean. Okay, so solving for this arc, we need to find the radius and our angle first. So we have 45 degrees as our angle. So we can convert 45 degrees into radians. Okay, so class, when we are using this formula, okay, or simply this formula, these are just from the both same formula. When we are using the same this kind of formula, we have to convert always our theta into radians. We can't use this formula if our angle is in degrees. Okay, so please remember that if you are using this S is equal to theta r, or theta is equal to S over r, our theta should always be in radians. Okay, it shouldn't be in degrees, it should be in radians. So converting 45 degrees into radians, we have pi over 180 degrees. So dividing 45 and 180, so we can divide 180 by 45. So 180 divided by 45 is simply 4. So giving us pi all over 4 radians, or pi over 4 rad. And now since the ISS station is rotating above the Earth, so therefore, getting the total radius, we will simply add 6,400 plus 400, since this part will be our total radius. There, this will be our total radius, this length. Okay, so adding them, we will have 6,400. R is equal to 6,400 plus 400 is equal to 6,800 kilometers. So now we can use our formula wherein S is equal to theta r, wherein our theta, or our angle in radians, is simply pi over 4 rad, and our radius is 6,800 kilometers. So solving for it, again, for our arc, we can multiply 6,800 by 400. We can divide this. So we have, when we divide 6,800 by 4, giving us 128 divided by 4, we will get 7. So we will have 1,700 kilometers, or simply 1,700 times pi kilometers. So if we try to use our calculators, okay, so getting the exact answer, we will get 5,340.707, or simply, since the problem tasked us to convert it to the nearest kilometer, so we will get 5,341 kilometers. So this will be our final answer for this problem. Next, a circular sector, or S, is a figure formed by two radii and an arc. Okay, so this one is the sector. So this, from our figure a while ago, so this one, this orange part, is our arc. Okay, while this total area inside, will be our sector. Okay, so don't be confused. The arc is simply part of the circumference, while the area inside the two radius and the arc is what we call our sector, or our circular sector. So area of the circular sector, the area is given by the formula A is equal to 1/2 RS, or simply 1/2 times the radius and our arc length. So while the length of the circular arc is given by S equal to R theta. So this was discussed a while ago. Okay. So A is equal to 1/2 R theta. So if we try to substitute, so we need to try to substitute A all over 1/2 RS. So we know that S is equal to R theta. So when we try to substitute this value into this value, we will get 1/2 R times our R theta. So therefore, the area is also equal to 1/2 R squared theta. So again, theta should always be in radians, okay? So this, we are tasked, suppose a sprinkler head sprays to water the grass of a lawn. So let us copy this part so that we will have a guide. So this problem, it states that suppose a sprinkler head sprays the water to water the grass of a lawn. If a sprinkler head rotates 90 degrees and has enough pressure to keep a constant 25-foot spray, what is the area of the sector of the lawn that gets watered? So it is given first. Let us first write all our given. So this given that we have an angle, so that the angle is theta is equal to 90 degrees, and then it has enough pressure to keep a constant 25-foot spray. Okay, so therefore if our center is the spray, the sprinkler, again the total length that the spray can achieve is 25 foot or 25 feet. Okay, so 25 feet. So therefore, this length or our radius is our 25 feet. Okay? So radius R is equal to 25 feet. So now, what is the area of the sector of the lawn that gets watered? Then your answer to the nearest square foot or square feet. Yeah, square feet. Yeah. So now, we are tasked to find for the area of the sector. Okay? Or circular sector. So this is denoted by S. We need to find the area. So again, from our formula, we have the formula A is equal to 1/2 R squared theta. So now we can't use this because we don't have the value of S. Okay? We don't have the value of the arc length. However, we can still solve for the arc length, but it would be too studious. Okay? So since we have this value or we have this formula, we can directly use it. However, again, our angle should be in radians. So converting 90 degrees into radians, so we have 90 degrees. So for every 1 pi radians, we have 180 degrees. It should be on the other way around. Okay, so we will have pi over 2 radians. So from this, we can now use this as our angle. So we have 1/2, and it's given that our R squared or our radius or the length that the spray can achieve is 25 feet. Okay, so I have 25 times our theta, which is pi over 2 radians. 25 feet times pi over 2 rad. So this will give us simply pi over 4, 25 pi over 4 radians. So if we use our calculator solving for the exact value of 25 pi over 4, sorry, this should be in squared, sorry. So our formula is 1/2 R squared theta, so this one should be squared. So we'll get pi over 4. So 25 squared is simply 625. So we can write this 625 pi all over 4 radians, or 4 feet squared, So this, if we get the exact value of it, we get 490.87 And since we have to round it up on the nearest foot or nearest feet, we simply convert it to 491 square feet. So this will be our final answer. So next, we will now discuss linear and angular speed. So definition of linear and angular speed of a point moving on a circular path. A point moves on a circular path with radius r at a constant rate of theta radians per unit of time. Its linear speed is equal to v is equal to s over t. Or the v, simply our velocity. Or v is equal to s over t. Okay? Wherein s is our arc length and t is our time. Okay? S over t. So where s is the distance the point travels, or our distance or length, and then given by s equal to r theta, we can also point the angular speed is equal to omega is equal to theta all over t. So this is just simply, they are both simply solving for speed or velocity. However, this formula is for linear speed and this one is for angular or circular velocity. So linear speed given angular velocity or speed, we will get v is equal to omega r. So a problem, it stated that a car at a constant speed, so let us use these formulas. So we have a car at a constant speed around a circular track with circumference equal to 2 miles. If the car record of a time of 15 minutes for 9 laps, what is the linear speed of the car in miles per hour? So we have our distance, or our s is equal to 2 miles. Next, if the car records a total time of 15 minutes, so we have t is equal to 15 minutes. So from our given, and it is stated that we have to find the linear speed. So we have s, or our distance, we have t as our time. So solving for v, our velocity, let us use first this formula. So we have v is equal simply to s over t, wherein s is denoted as our distance. So we have 2 miles divided by 15 minutes. So this is just simply 2 miles per 15 minutes, or if we use our calculators, we will get, so since, it is stated that it has 9 laps, okay? It is stated that 15 minutes for 9 laps. So for every lap, for every lap that a circular track, it is equal to 2 miles. So we have 2 miles times 9 laps. So we have a total of 18 miles. So therefore, our total distance should be equal to 18 miles all over 15 minutes. So now solving for our velocity using our calculators, we just simply divide 18 by 15. We will get 18 by 15, it will be miles per minute, okay? However, it is stated that in the problem, it should be in miles per hour. So we convert minutes to hours. So we have, for every 1 hour, we have 60 minutes. So we can cancel out 60. We can cancel out the minutes. So we can also divide this by 15. And this is also divisible by 15. Giving us 60 divided by 15 is equal to 4. So we have 18 times 4. So we have, when we multiply 18 times 4, it will yield to 72. So therefore, our final units are miles and hours. So therefore, we have 72 miles per hour. So this will be our answer for this problem. Next, a lighthouse in the middle of a channel rotates its light in a circular motion with constant speed. If the beacon of light completes one rotation every 10 seconds, what is the angular speed of the beacon in radians per minute? So again, we have our time. which is equal to 10 seconds. And next we have we don't have any other values, okay? So for us to solve for this problem, okay, we need to analyze what this one rotation means, okay? So again, for every one rotation, so what is the value of our angle? So we can simply write it as an angle. So we have 360 degrees, okay, for one rotation of a circular motion. However, using our formulas again, we should convert it into radians. So 360 degrees is also equal to 2 pi radians. And now we are tasked to find the angular speed. So the angular speed is denoted by the Greek letter omega. So from our formulas, we can solve for omega using this formula. We have omega is equal to theta over t, wherein our theta is equal to 2 pi radians and our t is equal to 10 seconds. However, we need to find it in radians per minute. So we have to convert these 10 seconds into minutes. So we all know that for every 60 seconds, we have 1 minute. So we can convert this, so we can cancel the seconds. So we can also divide this by 10. We have 1 divide this by 10, we will get 6. So now we can get for our angular speed, we have 2 pi times 6 is equal to 12 pi radians per second. So if we convert it into numerical value, removing the pi, we will get, so this will be our final answer. So if we try to convert it, so let's try to convert it. Inputting it in our calculator, we get 12 pi, this should be 12 pi. 12 pi rad per second. So we get 12 pi. This is equal to 37.699 radians per second. Radians per minute, sorry. It should be in minute. So this is just these two answers are just the same. Next, for number 3. For number 3, a Ford F-150 truck comes standard with tires that have a diameter of 25.7 inches. If the owner decides to upgrade the tires to a diameter of 20.82 inches without having the onboard computer updated, how fast will the truck actually be traveling when the speedometer reads 75 miles per hour? So first, let us write all the given that we have. So the original diameter, so we can D1, our first diameter is 25.7 inches. And for D2, we have our given as 28.2 inches. And next, we have if the speedometer reads or their velocity, V, our V is equal to 75 miles per hour. So first, to solve for this problem, we must first determine the angular speed of the original truck, original tire. So why do we have to find the original angular speed? Since this angular speed, this will also be used for our new tires. Again, it is stated that in the problem, without having the onboard computer updated. So therefore, the angular speed for both scenarios or for both tires would be the same. So we must first find the angular speed for the original tire. Since the given speed in this problem is when we are using the original tires. Okay? So, using our formula again, so let us go back. So, we have to find omega, we can have our V is equal to W over R. So, why is this so? So, we have V. So, let us write our formula. V is equal to omega over R. So, we have V, but we still don't have R. Again, we have the diameter of our car, or our tire, I mean. So if we have the diameter, we can get our radius. So again, the radius is simply half of the diameter. So our R is simply 25.7 over 2. So leave it as is. So now we can solve for omega. So let us first transpose our formula. So to solve for this, this will be in inches. So now let us solve for our velocity. So for our angular velocity. So first let us isolate the angular velocity. We divide both sides by r, giving us omega is equal to v over r. Now since omega is equal to v over r, we can now substitute our values. But first, let us check our units. So in our units, miles, our units for velocity is miles per hour, and for our radius is in inches. So let us convert one of them. So we all know, so let us recall, for every 1 mile, we have 5,280 feet. And for every 1 foot, we have 12 inches. So multiplying 5 to 80 by 12 inches, we get 63,360 inches. So from this, we can use this as our conversion factor. So for our velocity, so writing our velocity, omega is equal to v over r. So we have for our velocity, okay, so let's first write our numerator. We have 75 miles per hour. And we first need to convert it. Now we have, for every 1 mile, we have 63,360 inches. Then our radius is given, is solved from the diameter. We have 25.7 over 2 inches. So now we can cancel out our miles, leaving us inches per hour, so that we can solve for our omega. So dividing this, we will get 75 times 63,360 all over our radius, which is 25.7 over 2. So we will get 369,805.4475 radians per hour. Now that we have our angular speed, we can now use this to solve for our velocity when the tire is changed. Okay, so again, we have v is equal to omega over r. So now we are tasked to find the velocity. So we have our omega, but we still don't have our r. Again, our d2 is 28.2. So therefore, our r2 is simply 28.2 over 2. If we try to simplify this so that we won't have any fraction, it is equal to 14.1 inches. So now we can solve for our velocity. So we have v is equal to omega, which is 369,805.4475 radians per hour. We can now multiply this value of the omega to our radius, which is 14.1 inches. Solving for this, we will get, so this will be our answer. So answer is equal to 369,805. So answer times 14.1 inches. So therefore, the new velocity that we'll have is 521,214,256.809 inches. Okay? Inches per hour. So now, let us try to convert this velocity into miles per hour. Again, for every 1 mile, we have 63,360 inches. So from this, let us divide this given answer. So our answer is 5,214,256. So dividing it by our 63,360, we will get that our speed in miles per hour is 82.30 miles per hour. So if we increase the radius or the diameter of our tire, even though that the reading in our speedometer is 75 miles per hour, since it is not a standard car, therefore our new value for our speed is 82.30 miles per hour. It will be faster since the radius of the tire is bigger. So therefore, that is our lesson 1.